Talking about Windows NT and you're talking about applications. When you get into the kernel, when you start developing applications like file system and you're writing kernel mode code, the worm turns. We expect the code that you write to be of the quality that Windows NT itself is, and we are unforgiving if it is not, meaning the machine will crash. End of story. That means you have to be very, very diligent in your implementation and very, very diligent in your testing. As diligent as we are. All right. For Windows NT, I think I can safely say that it's as robust an operating system as I've seen available on the planet. So I think I can say that safely and not be contradicted. This puts the onus of responsibility for stuff on you guys. If the system should crash, and the last thing on the stack is, in fact, your file system, our support people are going to say, looks like the last thing on the stack is your file system, and point back at you as the possible culprits. That doesn't necessarily mean that it's always your fault, but in general, we spent a lot of time and a lot of effort testing the internals of Windows NT, and we kind of would really like it if you did the same thing for your file systems. So we're trying to bring a new level of quality to Windows NT, and we'd like it if you and your implementations did the same thing. All that said, Darryl's now going to drill down into the I/O system. His voice is starting to go a little bit, so he's still fighting a fairly nasty cold that he's picked up overseas. And without further ado, here's Darryl to talk about the I/O system. We'll have a little instructional. If you want to draw pictures, you need to come down and click on that little icon there. It happens when the mouse moves. Then you can draw pictures. And if you hit E, you erase.
I'd like to, is this thing on? Yeah, okay. I'd like to expand on what Dave said. If you're anywhere on the stack, we're going to blame you. No. So we're going to pretend that I had this red shirt on this morning so you can ask me questions. I didn't get it in time, and I didn't feel like everyone would watch me change. Okay, so let's talk about the I/O system. In this talk, one of the things that I'm going to try and do is I'm going to try and give you a quick overview of what the I/O system looks like. I'm also going to talk about device drivers and how they work, because I think it's really important, regardless of what kind of file system you're writing, whether it's a network, you're going to talk to transport drivers and you're going to talk to NDisk drivers, or if you're an on-disk file system, you still have to talk to device drivers. It's really important to have an understanding of what those things are actually doing underneath you so that you understand how you interact with them. Whoops. That was great.
Well, I showed him how to draw pictures now.
So how do I get off this slide? Go back to the corner and click. It's still drawing.
Now you go back and put it down.
I don't think I'm going to draw anymore. Okay. Okay, so there's the Windows NT system structure. We just talked about that. I'm not going to cover it again. Here's the executive. This particular talk will cover all the things that are highlighted: the I/O system, file systems, device driver. You should note that they're all in kernel mode, and as Dave said, we kind of open ourselves up to your code. Okay, is to say, if someone asked some questions earlier during the break about, boy, I guess there's a lot of questions too. So I'm going to try and make myself available as much as I possibly can to answer your questions. But someone asked me some questions about what's the difference between trapping through a ZW and calling an NT API directly from within a file system. And one of the things that I was talking about was how we probe arguments inside the executive. And the way that happens is if you cross this line into the Windows NT executive, So you've been from user mode. The way we do that is we do that with a trap. So the previous mode is now user, and the current mode is now kernel. When I go inside the I/O system to determine, or any of these Windows NT Executive APIs, anytime that we want to know, can I actually touch this variable? The way we ask that question is, was the previous mode something other than kernel? If the answer to that question is yes, i.e. it was user mode, then we're going to go off and we're going to probe the arguments. We're going to make sure that they're really in an address space that the user could touch. We're going to make sure they're valid. They're not in some no access page, or the person's trying to do something that's going to cause the system to crash. If you're in kernel mode, that is, the answer to that question is no, it wasn't user mode, it's kernel mode. I don't even bother to look. Okay, so if you call me and you pass me some bogus arguments, the system's going down, period. No two ways about it, okay? We trust your code as much as we trust our code. We don't want to spend the time going and probing all the arguments that you just passed me to make sure we can touch them, because that impedes on the performance of the system. Okay, so we just open ourselves up and we trust you just as much as we trust ourselves. Okay, so what does the I/O system look like? There are, in my mind, three components to the I/O system. First component is the system service APIs. That's the NT Executive APIs that are the interface from user mode to kernel mode to get you into the I/O system in the first place. Then there's the I/O subsystem itself, which consists of all the I/O subsystem calls that you can make and that other drivers can make. And then there's the driver interface itself. That is, how does the I/O system talk to drivers and make drivers part of the I/O system? Okay. If you made a diagram of what that looks like, the top of this picture then is the I/O system services, and therefore the top of that is the line that goes from user mode to kernel modes. The only way that you can get to a device driver or the I/O subsystem is to come through this set of APIs. We trap to get there from user mode, so we just transition from user mode to kernel mode. The left-hand side represents all the I/O calls, and the right-hand side represents all the device drivers and file systems and et cetera, that exist in the system to help make up everything that has anything to do with something that comes into the system or goes out of the system. Okay, so the I/O system is all of that all at once. To talk about the NT APIs, the system services themselves, there are synchronous and optionally asynchronous interfaces at that level. That is to say that if you're a subsystem sitting on top of NT and you're trying to emulate another operating system interface, these are the system services that you use, and there are synchronous ones and there are asynchronous ones. The ones that are asynchronous, you can either open the file object in a way that says, I would like everything to be synchronous, or for those APIs that I can call asynchronously, I like you to actually make those synchronous as well. The system service, all the system service APIs operate on file handles. Again, this is one of these handles that you get back from the object manager that I talked about in my earlier presentation. Completion notification for I/O operations is either through a file, that is, when you call the file system or the NT API, you say, here's the file handle for the file that I want to perform this operation on. Now you can wait on that file handle to get set to the signaled state, and when it's set to the signaled state, that means that your I/O operation is complete. Another way to look completion notification is via an event. You can associate an event with each particular I/O operation, and now you simply wait on the event. And when the event is set to the signaled state, that means the I/O operation is complete. Another way is to use an APC. That is to say, what you're going to do is you're going to post an I/O operation, and you tell the I/O system, when you're all finished performing this I/O operation, what I'd like you to do is call this routine, i.e. APC, asynchronous procedure call. And then the final way is something called a completion port. This is new for 3.5. What a completion port is you can think of it as a message queue. You create an I/O completion port and you associate that port with a particular file or set of files. And when you do that, you can give it a key. Now what happens is when the I/O operation is complete, the I/O system, rather than queuing an APC or setting an event or something, simply plunks a message inside this completion port that says this particular I/O operation is complete. And the way that it identifies to you, the waiter, is it gives it the key that you gave it for the file. It gives it a unique key that you gave it for the operation, gives you a pointer to the I/O status block that you provided so that you can find the status. What this allows you to do is have a whole pool of threads that do nothing except for sitting around and wait for I/O completion. Okay? Okay. All the system services operate on file sizes and offsets that are 64 bits. Okay, what are some of those things? We have services to create and open files. We have services to read and write data, query a directory, or to look for a change notification. A change notification simply means I want you to watch this directory, and if anyone ever makes the following types of changes to files within this directory, for example, I would like to watch for additions or deletions of files, then what I want you to do is complete this operation. And it gives you, optionally gives you back the name of the file that changed inside that directory. This is great things like the file manager. It can simply post these things to directories that it's displaying on the screen. And when it gets one, it goes and changes the screen, says, oh, this file's now gone, or this file now appeared. Or if you're displaying how big each file is, when one of them changes, you can actually go update the display, et cetera, et cetera. File information services, for example, how big is this file, where's the end of the file, et cetera, et cetera. Device and file system services, these are APIs that allow you, a file system writer or a device driver writer, to have an interface between your application and your driver that's not subsumed under read, write, or query, et cetera, et cetera. For example, you'd like your device to go offline, something like that. This allows you to extend the API set so that you can have an interface so that your application can tell your device to go offline or whatever. And then the I/O completion services, these are the completion notification ports that I just talked about, and then a bunch of miscellaneous services. The I/O subsystem itself is made up of the device driver support routines. These are all the I/O functions that device drivers call. File systems can call these as well. The I/O system service support routines, these are functions that the I/O system services themselves use to perform operations internally. And then file system driver support routines, which are support routines that are not exported to device drivers but are exported to file systems. There are a number of things that we'd like file system driver writers to be able to do that we don't want device driver writers to be able to do because they're just simply not appropriate. Wow. There's now at least 90 of these things. I think when I wrote this slide there were 60. And by the way, I should tell you that while I was gone, I got this message last night on the way home. I finally made it to the States where I had a phone that had a tone dialer, not a pulse dialer, like they've had in Italy and Spain, which is where I've been for the last week, so I couldn't get any messages. And I got this message that said, by the way, we changed and rearranged some of your talks. So this is the first time I've actually seen these slides, right? So apparently there are now 90 of these things, not 60. And there are at least that many. Some examples of some of the functions that you'll be calling are I/O call driver. I/O call driver is the I/O system function that you call when you want to call another driver. You don't actually call the driver directly. You call it via the I/O system. Another one is I/O complete request. Most of the time, if you're a file system, either you're going to go ahead and complete the I/O operation, and then you're going to tell the I/O system this operation is now complete, or you're going to pass that operation down to someone sitting underneath you, a transport or a device driver of some kind, and when they're all finished with the operation, they're going to tell you that the I/O operation is complete if you'd like to know about it. We do have the ability for a device driver to complete operation, and you can say, if it completed successfully, I don't even care. Okay, so we won't even tell you when it's complete. We just bubble it back out to the I/O system, and the I/O system takes care of the actual completion as far as the user application is concerned. IO build asynchronous FSD request is a way that you can build a file system driver request. It's asynchronous that you can pass down to a driver that sits beneath you and then not worry about it, and it will complete asynchronously. IO read partition table is a function that disk drivers use. Today, in other operating system environments, one of the things that seems to happen for some odd reason is all the device drivers, all the disk drivers in the world for DOS today have to go out and understand what a partition table looks like. And some of them don't agree with each other, and some of them just plain got it wrong. And there's no way to make partition tables extensible, because you can't change them because it's already built into all the device drivers. Well, one way to fix that is to make one single IO function, and now what you do is the device driver, when it comes during its initialization, creates an object that represents the entire device, and then calls the IO system and says, give me a list of where all the partitions are and how big they are. And it doesn't worry about what the structure on the disk actually looks like to go divide the thing up into separate partitions. Okay, by having it in one common place, we can in the future change what that looks like when we don't have to support DOS anymore. Right. IO start next packet. I talked a little bit about device queues this morning that the kernel gives us. IO start next packet is when you've completed the IO request packet that you're working on, you can call the IO system and say, go start the next packet in the device queue if there is one. And the IO system and the kernel work together to go determine whether or not there is one, and if there is, then it calls you back, and you go implement the next IO function. Okay, and then the driver interface. The driver interface are these IO functions, some of which I just showed you what they look like. IO operations operate on these objects. There are device objects and adapter objects and other types of objects, which I'll show you. Communication between the IO system and device drivers to other drivers and file system drivers is all via something called an IRP. An IRP, which is an IO request packet. Basically what happens when the user calls the IO system and says, I would like to perform this function, say a read operation, I'd like you to go out and read this many bytes from this particular device and put it in this particular buffer. The IO system builds an IO request packet and passes that to you, and we work together to communicate. This is how we communicate what the user was trying to do in the first place. Okay. So I mentioned IO call driver. This is how a driver calls another driver. Basically what happens is there's an IO request packet that represents this particular function, and in the IO request packet, that blue piece up here on the diagram represents the function code for the operation that the user wanted to perform. For example, a read. So there'd be an IRP code of a major function code of read, and a pointer to a device object, which is the device on which we'd like to go perform this read. So basically what IO call driver does is IO call driver takes the pointer to the device object and finds in it a pointer to the driver object that represents your driver in the system, and indexes into a table of dispatch routines which you filled in during your driver's initialization, and finds the function that we're supposed to use for read, and that's the dispatch routine. So that's how IO call driver works. Okay? Okay, from the IO system's point of view, externally there are two different types of objects that we export. The first one is a file object. A file object is the basic object on which you perform all IO operations. Behind that file object can be anything that you'd like to make it. It can be a file. It can be a directory. It could be a device. It could be an entire volume. It could be a whole bunch of volumes in the case of a jukebox. It could be a mail slot or a name pipe, a virtual terminal, anything that you'd like to make it. Okay? But from the user's point of view, from an NTAPI point of view, all of that's represented by a file. And all the operations that are performed on that file object. Okay? So we do all the security stuff right up front. figure out who the person is, whether or not they can perform the operations that they've asked for, the desired access that they've asked for. If they can, then we create one of these file objects. There's one file object for every open instantiation of the actual object that's being operated on. Okay? So if I'm a process, let's say I'm a thread. I'm thread A. And thread A says, IO system, I would like to open the file foo. What happens is I get back a handle to it. That same thread, thread A, if thread A says, I would like to open the file foo, it gets another file handle to another file object. There's no shared state at the object level between those two file objects. Okay? Okay, there are ways to share that information, but every time you open a device or a file or volume or whatever have you, you're always going to get a new file handle to a new file object instantiation. Okay, the second type of object that's exported is the completion object, and those are the ones that we talked about before. This allows you to have a pool of threads that sit around and wait for IO completion to occur on files, and then they just handle all the completion. Okay, that was externally. Internally, things that you folks need to worry about, the things that you folks actually need to worry about as file system writers are really the first two. I'll talk about all five. The other three, controller objects, adapter objects, and interrupt objects, are really for device drivers, not for file system writers. So you're not going to have to worry too much about them, but I'll explain them. The first one is a driver object. A driver object represents to the I/O system and to the system itself where your driver is actually loaded in the system. It says where it's loaded, how big it is, where all your entry points are, and some other information that I in the I/O system need to keep track of in terms of where your driver is. You will be responsible when you get called during your initialization routine to fill in some of the information in the driver object so that I can find, for example, your read routine or your write routine. All of the dispatch entries are pre-filled in by me before I call you in your initialization routine to point to a routine that says, if you ever get here with this type of I/O request, it's simply an invalid I/O request for this type of device. So if you're writing a printer driver, the read function for the printer driver is going to say, this is an invalid request. You don't need to do anything about it. You don't need to supply any function. You just fill in the write request or whatever request that you need to do. Okay, the device object is an object that represents the physical, logical, or virtual device to the system. These are generally named objects, but in some cases they're not. They represent the actual physical devices on the system. Is the simplest way to think about it. It will get more complicated than that later, especially if you're writing a mass storage file system, but we'll handle it when we get there. A device object has the device independent section, which I control, and the device dependent section, which you control. That is to say that there's information that you need to keep about the global state of each of the devices that you're handling in the system. You get to define what all that looks like. Okay? I get to define what the common part looks like. For example, I need to be able to find your driver when someone says IO call driver and passes me a pointer to the IRP in the device. This is how I do that. Okay. Quickly, a controller object represents a hardware controller to an IO system, to the IO system. These are not visible outside of the IO system. You don't generally need to worry about them. This is a synchronization mechanism that a device driver can use. For example, let's say that I'm an AT disk controller driver. So I have two devices hanging off a single controller. When one of those devices is busy performing an operation that uses the controller, the other device can't be used. Okay? If I'm doing a read through one of them, through to a device on this controller, I can only use that path for one. This allows the device driver writer to provide a synchronization mechanism so that he knows automatically that that other device is currently using the controller and he has to wait. And we handle all that for the device driver. The same thing's true of an adapter object. An adapter object represents the hardware mapping register and our DMA controller in the system so that different drivers having different controllers or devices sitting on the same DMA controller can use that as a synchronization point, okay? And that all happens automatically. And then finally, there's the interrupt object, which is provided by the kernel. It allows the device driver to associate an interrupt service routine with a particular interrupt vector for the system on a particular bus. Some of the machines that are coming down the pipe that you're going to see have an ESA bus hanging off of some other kind of bus, hanging off of some other kind of bus, hanging off of the I/O bus, which is separate from memory, and on and on and on. This allows us to pinpoint which device on which bus at what interrupt vector is associated with the interrupt service routine, so we can find that interrupt service routine to handle that device when the interrupt actually comes in. This also allows device driver writer to synchronize the execution of a function with that interrupt service routine. I explained that earlier during my previous presentation when I was talking about the interrupt object. Okay, so what does the driver model actually look like? First of all, drivers in NT can be loaded and unloaded dynamically or during boot. Okay, so when the system boots up, we're going to go out and we're going to load the minimum number of drivers we need to load in order to be able to get to all the other drivers and all the stuff that we need to load the kernel. Okay? Once the system's up, you can load other drivers or dynamically unload those drivers as you will. Note, however, that there are some drivers that you can't unload. Like, you can't unload the disk driver for the disk that you booted off of. That doesn't work very well. Another driver that you can't unload is while you're sitting there on the screen and you have a little mouse and you point and you say, see that video driver right there that I'm using to point to the screen? Unload it. That doesn't work too well because now you have no way of loading a guy to drive the video because you just unloaded the guy that you were using. Stuff like that. In general, file systems for mass storage devices aren't unloadable. That is to say, it's very difficult for device drivers to synchronize their execution in such a way that A, they know that they're not handling the device that was booted from, B, they're not on the path of any file system that was loaded, and C, finding all the volumes that you have mounted and synchronizing, closing all the handles to all the files for all the volumes that you're currently handling and making sure that no one slides in while you're trying to do that and opens another one is very difficult. In the future, however, we would like to make these things unloadable and we'll be working toward that goal. File systems can get very large depending on what you're doing. Obviously, if your file system supports logging and encryption and all the other stuff, compression, your file system may get pretty big and you may want to make it go away. There are two types of drivers as far as the I/O system is concerned, and the distinction between device drivers and file system drivers is getting smaller and smaller and smaller with each release. As we go through this, I'll kind of talk about, well, that's not real true, and I'll point to the places where that's becoming less and less of the case. But you will see the term FSD, and what that means is a file system driver. Device drivers operate in a limited context. That is to say, when the I/O system is called and it creates an I/O request packet, it calls the device driver. The device driver cannot guarantee that it's in the context of the calling process because there may be a file system sitting on top of it that queued the I/O request to our worker thread. Okay? It now doesn't even have the ability to go directly access, necessarily, the buffer that the user wanted to read the information into or write the information out of. Okay? So we have to be very careful about how we deal with this. They execute in the context of the calling thread sometimes, execute in the context of an interrupt service routine sometimes, and they execute in the context of a DPC routine sometimes. Okay? So they have a very limited context. File system drivers have the same interface from the point of view of what dispatch routines they can implement as a device driver. There's nothing to stop a device driver from saying, I implement query directory. There's nothing to do that. If they want to say they want to fill that thing in, and a user comes along and says, query the directory on this device, and the device driver knows how to handle that, they can do that, just like a file system driver does. Same thing for file locks or read or write or what have you. The file system driver, however, makes extensive use of something we call fast I/O calls for synchronous I/O. If you look at the I/O system started out being 100% asynchronous. Every single operation, including open, was asynchronous. Every single operation was represented by an I/O request packet. That is to say, every single time a user called us, I created an I/O request packet. If you look at the interfaces sitting on top of Windows NT, however, what have you got? You have DOS, you have OS2, you have POSIX, and you have Win32. 99% of all of those interfaces are synchronous. So what we wanted to do is we wanted to optimize for the case where it really was synchronous. So what we did was we invented something called the fast I/O or turbo I/O path. And that's the turbo I/O is something you'll hear every once in a while, but it's called the fast path inside the I/O system. What happens in this case is we come into the I/O system from the user. The user says, I want to perform this operation. The I/O system calls the object manager with the file handle, translates into a pointer to a file object, and asks the question, can this person do this operation? The answer to that question is yes. We probe the user's arguments, and then we ask the question, can we do a fast call on this operation? If the answer is yes, we simply call you directly, right inside the file system. Okay? We don't generate an I/O request packet in a particular case. This is different than device drivers. Device drivers don't generally perform fast I/O calls. Okay? By taking out all of the overhead of generating an I/O request packet, which means allocating it, initializing it, filling it all in, doing all the bookkeeping, and then calling you, and then you passing this thing all around, and then when you're all done, calling an I/O routine to complete that operation, queuing it, and getting back into the context of the thread, etc. It's synchronous, therefore, we can already tie up this thread. That is to say, this operation is synchronous, therefore, we're supposed to execute or implement this I/O operation while we're in the context of that thread. If we know that, we don't have to lock down any buffers. We're already able to touch them. We cannot leave the context of that thread. What happens then is for a read, you simply take all the information that you've cached ahead, plunk it into buffer, and say we're done by returning. I then take and return back to the user, and we're all finished. Okay, no I/O requests involved.